Hi, everyone. That was loud. Hola. No habla español. So this talk will be in English. My name is Seth, and I'm here today to talk to you about modern security with microservices in the cloud. For those of you that have never heard of me, I'm a developer advocate at Google. I previously worked at a company called HashiCorp, and I worked at a company called Chef before that. So I'm pretty active in open source communities. But today I'm here to talk about kind of security in general, and then there's a demo at the end. So traditional security, particularly like application security, revolves around this. I like this photo. You put a lock or a barrier around the entry point, and that's it. So when we think of infrastructure maybe 5 or 10 or 15 years ago, it looked something like this. You had some external load balancer that you owned, maybe like an F5 or some hardware load balancer, and that would hit some enterprise-grade firewall in your own data center that would do TLS termination, and then you would be in the secure area. And all transmissions between applications and services was generally trusted. And that was inside your data center. So we call this perimeter security. Once the request entered the domain, it was generally trusted. And this worked great whenever we had maybe 1 or 2 applications and 1 or 2 databases, and all of the communication was internal, and there was no third-party or external requests. But when we compare that to what a cloud environment might look like today, we have multiple networks. Some of them are virtual, some of them are physical. Some of them exist only in software. They're not actual hardware networks. We have many different services. Not only are they servicing external requests, meaning requests coming from the users, but they're also servicing internal requests from other applications and other services. Additionally, we might be using managed services. So instead of having our own database, we might be leveraging a hosted database, something like Cloud SQL or Amazon RDS. So we have to make API calls outside of our data center or across clouds to be able to talk to these external services that were previously in-house. And many of these lines go over the public internet, an untrusted entity. So in the cloud world, we are running on shared infrastructure. In a traditional data center, you own the server, the hardware, everything. But when we work into the cloud, we're running on shared infrastructure. Our applications might be running in the same server rack as a competitor. We can't really guarantee that, right? We can guarantee the VM isolation, the virtual machine isolation, but we can't have that segregation, that same separation of concerns that we have in a physical data center. As I said before, we're dealing with external users and internal services. So no longer is it just external request, TLS termination, application services, a response. We have inter-traffic communication, and that might be across different networks. Because of that, everything is inherently untrusted. You can't rely on the network or your VPC or your communication layer to be the ultimate security, because the moment someone penetrates that perimeter, they have all of the access. So services need to be authenticated, and they need to communicate with each other using things like mutual TLS or service-to-service authentication. But the things I want to talk about specifically are things like time-based credentials and revocable credentials. So in modern security, it doesn't matter how great our practices are or how much we've thought in advance. At the end of the day, attackers and hackers are very smart. They're going to find ideas into systems. They're going to exploit things that you don't have control over. Vulnerabilities in your programming language, like Ruby or Node or Python or Java, things that you can't control. So you need a system or a way to be able to respond to those vulnerabilities, not just patch, but how can you inspect your system? Did that vulnerability or that security hole in the programming language or the software that you were using lead you to be compromised, and how do you recover from that? And that's where time-based access controls and revocable access is really important. So the goal of this talk is to get you to stop thinking about security like this. Security is not a padlock, right? It's not just a thing that you secure and everything inside is untrusted. And start thinking about security like this. So this is a well-fortified castle. There's a moat. See, there's a moat. And there's lots of walls and hidden passages and trapdoors and all of these areas. So if an attacker penetrates the perimeter, it gets harder and harder and harder to eventually reach the customer critical or the business critical data. So we need to start thinking about what the security industry calls defense in depth. Get away from perimeter-based security and start thinking about defense in depth. And the cloud can actually help with this. So it's a bit of a double-edged sword. We have, cloud and microservices caused this, but it also helps with this. So for example, at Google and most cloud providers, we have a dedicated team of security people who are far smarter than I ever will be about security and thinking about these threats, both in the virtual world, the electronic world, and in the physical world. At Google, we have a project called Project Zero. You might have seen some of the things that we've released there. My question is always, are you as secure as a cloud provider if security is someone's part-time job? Right? So there are people who get paid full-time to think about these things, think about these threat vectors. If it's only someone's part-time job in your company to secure this infrastructure, you're likely not doing the same level of rigor. Cloud providers also have really cool physical security. So this is something that we often overlook as software developers and infrastructure people. We tend to think about software and systems and operations, but there's another part of security, which is physical access. The moment someone has physical access to your server or your data, a lot of promises go out the window. Right? You can't just take it offline, right? They have it physically in their hands. So physical security is a really important component of modern infrastructure security. So data centers have really cool stuff like cameras, laser beam intrusion detection systems, custom access cards, et cetera. Specifically within Google, we have this really cool hardware security. So we build all of our own stuff at Google. We run our own fiber, we build our own hardware, we have our own custom boot modules and our custom chips. And the reason for that is that, one, it makes us so that we're not susceptible to a vulnerability in the pipeline. So if a government or an agency was able to compromise a chip manufacturer and say, can you introduce this backdoor? We manufacture those ourselves, so we're not responsible for that. We don't have to incur the vulnerability downstream. Additionally, because we build all our own hardware, we can verify system integrity at boot. So if someone in the data center, which again is physically hard to access, has tampered with that server, it will refuse to boot. A lot of cloud providers have really cool services like automated vulnerability scanning. They'll do this through like anomaly detection, through machine learning, and then oftentimes they'll expose this to you as an API, so you can do this at your service level or your application level. So the security space is changing rapidly from people banging on keyboards to physical security, but also social engineering. You could sit and you could try to brute force whatever AES 256 CBC algorithm, or you could convince an employee to give you their password, and that's a lot easier actually. If you look at any major telecom, they've all been hacked recently, or people have been able to escalate privilege just by saying, oh, I am so-and-so, please can you reset my password and change my email, right? So social engineering is actually a huge vector for security, and it doesn't matter how great your systems are and how secure everything is, if at the end of the day there's an employee who can be tricked into performing a malicious operation. So what are the features of modern security then? Like, how do we prevent all of this? Well, the first one's pretty straightforward, and it's encryption. Encryption everywhere. That one's obviously straightforward. This is encryption in transit and at rest. So at Google Cloud, we encrypt everything you give us at rest by default. You don't have to do anything. It's on by default. Encryption in transit, that's using things like TLS, right? So if we're going over the public internet, we need to be sure that we're not only encrypting the data, but verifying the signature. By a show of hands, how many people have ever disabled TLS verification? There's more of you. I know there's more of you. You're lying, right? So when we do that, we're still getting the encryption benefits of TLS, but we can't verify that the entity we're talking to is correct, right? So we're still vulnerable to an attack where someone could impersonate that server. So even though the internet, the people listening on the network, couldn't see the transmission, we might be giving our data to an unauthorized party or service. We also need dynamic, time-based, and revocable credentials. What do I mean by credentials? I mean things like database passwords, user logins, multi-factor authentication, etc. And we need to be able to map credentials directly to a user or an owner. So today, it's very common to generate a database password, say like Postgres or MySQL, and you put that in a config file, and every application or instance of that application shares the same password. And this is problematic. This is a problem because if that application gets compromised, there's only one credential. We can't trace it back. We can't look at our logs and perform an analysis. Additionally, we have this very small, or this very large surface area for an attack because these credentials tend to be long-lived because they're difficult to generate. Another feature of modern security is this requirement for a unified API and codified or captured as code best practices. And the reason for this is that if we want non-security professionals to take security seriously, so if we want people who don't generally think about security to start caring, we have to make it very easy. I can't have engineers on my team decide which CBC cipher to use. I can't have them pick the latest and greatest algorithm. Instead, I need to give them an API. I cannot expect everyone to have a doctorate degree in cryptology and cryptography to be able to utilize my service, right? If I'm a Ruby developer or a Python developer, I just want to say encrypt this and decrypt it, and I don't want to think about cipher suites, et cetera. So if we want developers and engineers and software engineers to take security seriously, we have to make it easy. And that's why having an API and a centralized service where we can capture the security best practices in a single manner is a really good idea. And that's really what Vault is designed to do. So Vault is an open source tool from HashiCorp. It generates secrets. It tries to be this centralized secret store, or the secretized storage management system. It runs on any platform. It's a single static Go binary. But instead of talking about it, I decided that I'm just going to show you. So who's excited? That was not exciting. Who's excited? All right, I'm not texting. I'm getting my cheat sheet. All right, cool. So this is a terminal that you can't see. All right, cool. All right, awesome. So the first thing I'm going to do is I'm going to start a Vault server. The way I do that is I run vault server -dev. This started a Vault server. It's actually that easy. I don't have any magic things configured. You download it, you install it into your path, and you run vault server -dev. So I'm going to open up a new tab here that's running in the background. And Vault is very similar to like a web application. So just like Twitter or Facebook, you have to log in, right? You have to give a username and a password. But because Vault is a service, it's an application service, there's a number of different ways we can authenticate. We can authenticate via a token, which is like a session ID. We can authenticate via username and password. We can authenticate via something like a GitHub access token, et cetera. And when that happens, we get a session in Vault. So I'm going to go ahead and log in as the root user. Root. So at this point, I'm kind of like the super user in Vault, and I can do anything that I want to do. And this is because this is a brand new Vault server. There's no configuration. So the first thing I'm going to do is I'm going to go ahead and create some users. Scripts. Wow. I guess it helps if I'm in the right directory, huh? So I'll create some users. So what I did here is I created a policy. show you this real quick. This is mostly because I'm bad at typing. I created a policy, and we'll talk about that in a second. And then I enabled username and password authentication, and I created these 4 users, Sally, Bobby, Chris, and Devin. And I gave them the ability to log into Vault just with their username, and the password is password. So obviously not best practices security here. Or maybe it is, I don't know. So the first thing that Vault is it's a static secret store. So you can think of this as like encrypted Redis or encrypted memcached. You give Vault some data, Vault encrypts it in transit with TLS and at rest. It gets stored in Vault's storage backend, which in this case is just the file system. So on the file system, I'll have like a blob of encrypted data. When I want to get that data back, I ask Vault. Vault decrypts it and gives me the plain text data back, assuming that I'm authenticated. So this whole process revolves around authentication. So what I'll do here is I'll Vault kv put secret foo, and I'll just say Wi-Fi equals hello Wi-Fi. So that's not the Wi-Fi password, but it could be. And we'll see here we get some metadata back. So this is stored on my file system now. When I want to retrieve that back, I just get secret foo. I'll clear the screen here. And you can see that I get some metadata back, but then down here at the bottom, I have that Wi-Fi as hello Wi-Fi. So how many people feel more secure? Yeah, so I always like to talk about this because as an industry, we've been conditioned to believe that security is hard. We've been conditioned to believe that it has to be painful or difficult to be secure. And that's not the case. Vault has been audited. It has been reviewed by many different compliance firms, and it always passes with flying colors. So this is secure. It may not feel that way, but it is. And the KV store supports basic Crud operations: create, read, update, and delete, as well as list. So I can, add another value here. I can just say, Vault kv put, and you can see it's versioned, and then I can read that value back out. So C equals D, but if I wanted to get the original one back, I can ask for the first version, and we'll get our original Wi-Fi password. So it's just a versioned key value store, but at the end of the day, it's encrypted in transit and at rest. That's not exciting, but it is cool. It's great for a number of things. Vault also shines in the fact that it is a secret solution. It's designed to be this centralized secrets management store. How many people have ever written an encryption service before? How many people want to? Exactly. OK, there's like 2 people. Well, this talk is not for you. So what Vault aims to do is, instead of having each team in each language, Ruby, Python, Java, Node, Go, whatever, write this encryption and hope they get it right, Vault provides encryption as an API. This is similar to something like Amazon KMS or Google KMS, where you give Vault data, but instead of Vault encrypting the data and storing it locally, it encrypts the data and gives it back to you. So then you store it somewhere. It's your responsibility as the person making the request. And we call this the transit backend in Vault. So what I do is I enable the backend, and then I create a key. So Vault write transit keys my app. So what I've done here is Vault has created an encryption key that is kind of like a symlink or a pointer to my app. So my app is just a human-friendly name that points to this encryption key. So whenever I want to encrypt data, I just give Vault that encrypted data and the name of the key. So I write to transit encrypt. I told you I couldn't type. And then I give it some plain text data. So the plain text data I want to give will be, hello scaleconf. But I actually have to base64 encode this data. And the reason for that is that Vault can encrypt more than just text. So if you imagine that was like a PDF or a Word document or something like that, I can't transmit that over HTTP as is, because it's a binary file format. So I base64 encode it so that it's transmittable. And then I get this ciphertext back. So this ciphertext is what I would store in my database, my file system, my application, whatever. And this is encrypted. And if an attacker doesn't have access to Vault or privilege in Vault, that's it. That's a string. They can try to brute force it, but I think it takes like 256 years with modern technology, so good luck. I can decrypt this, though. Transit decrypt my app. And this time I give it the ciphertext, so I'll give it that string that it gave me back. And it gives me back not hello scaleconf. But that's OK, because it's base64 encoded. So you thought I messed up, but I didn't. So this is really scalable. So the most common interaction with the transit backend is something like databases. Vault's general, like KV store, you don't want to put a bunch of data in there. But with this, Vault is only managing the underlying encryption keys. So this scales. If you imagine you had a database of hundreds of millions of rows or hundreds of millions of users, you can actually just have one key or one key ring that's managing all of that data. So it's significantly more scalable that way. Speaking of databases, though, where Vault really shines is its ability to generate dynamic credentials. So right now, most organizations generate database credentials by logging into the server, running some commands, copying and pasting the username and password into a text file, and forgetting about it. How many people, is that your process? Yeah, see, it's real. If you work for a startup, it's a little bit different. You Google, how do I create a credential? And then you go to Stack Overflow, and then you copy and paste the code. But same process. Enterprises fill out a Jira ticket. So I'm going to go ahead and enable the secrets database, the database secrets engine. And what this does is it configures Vault with basically like the root user or the privileged user of my database. And then it grants Vault privilege to generate dynamic users on the fly. So this will make a little bit more sense when I show it to you. So again, because I'm terrible at typing, I have this shell script here. So I'll show it to you first. So the first thing that's happening is we're configuring Vault. We're saying, hey, talk to Postgres on this connection URL. So I'm running Postgres locally. And since I'm running on localhost, I don't have SSL. And then I'm telling Vault to create a role. A role is like a mapping between a name. So this role is called read-only. And this is the SQL that Vault is going to fill in. So whenever Vault runs, it's going to run this SQL against Postgres, and it'll fill in the name, expiration, and password automatically. And it'll generate those on the fly. So let me first start Postgres. So I have Postgres running on Docker now. And now I will configure, what do I call this? Configure database. Cool. All of this is ready now. So what I did is Vault has this root credential, and it has some SQL that it's going to run to generate users. So when I want to generate a user, all I do is read from the path. So remember that read-only here is just the name of the SQL. It's just like a pointer or a reference to the name of the SQL that's being run. So what happened here was I made that API request to Vault. Vault connected to Postgres. It executed SQL, filling in a username, a password, and an expiration that was dynamically generated. So unlike regular Postgres credentials, these credentials expire in an hour. So if I do nothing, in an hour, this credential expires. That prevents secret sprawl. This username and password is dynamically generated, meaning Vault generates that value automatically. Let me just make this a little bit smaller. So each time I read from this path, you can see that I'm getting a new username and a new password. So they look the same, but the username and password are different. They're both high entropy values. That username and that password is a real Postgres login. You can log into Postgres with that. So if I do PSQL -u Postgres. So if I look at all of the users in this database, you can see that there's 1, 2, 3 users. And that's because I ran this command 3 times. So if you imagine your application boots, and instead of looking at a config file to get its database credentials, it makes an API call to Vault, and it gets a unique set of database credentials that only it knows. That means that when you're looking at your logging and your alerting, if that credential is compromised, you know that that application was compromised, because it's the only thing that knows about that credential. I have to look at my phone so it'll unlock. All right. So what happens if something bad goes wrong, right? So I said before that it's not just about preventing these things, it's about how do you respond to them. So what I'm going to do here is I have this other script that I wrote that is going to go through and generate a bunch of database credentials. Basically what it did is it's designed to kind of showcase what this would look like if it was running in production. And remember that we have those 4 users. So if I run Postgres now, I'm going to cheat. You'll see that I have significantly more users in here. And this would simulate like a production environment with many different microservices. So what happens if one of my employees is not good anymore? So let's say that Chris, for whatever reason, is no longer with the company. I need to make sure that any operation that Chris did is no longer trusted. Because Chris could have like generated himself a bunch of credentials or herself a bunch of credentials before they left the company, and I don't have a way to trace that. With Vault, it's very easy to just revoke everything that Chris ever did. So I can come in here and I can say Vault token revoke mode equals path. And what I'm going to do is I'm going to revoke every authentication that Chris ever made, which is going to revoke every credential that he ever generated. So I'm going to say auth user pass users Chris. So this will, what this is going to do is this will revoke the token, and then in the background, Vault will actually go and revoke every credential that Chris ever created, and that includes those database credentials. But what happens if it's not just Chris? What happens if I had a huge vulnerability and I just want to untrust everything? Well, I can do that. I can do Vault least revoke, and I can revoke all of the database credentials. And you'll notice that took a little bit longer, but now when I run du, there's no users besides the built-in Postgres user. So Vault revoked all of those credentials automatically. So if you imagine you're in the middle of a security incident, instead of fumbling with the keyboard, it's just Vault revoke. So the last thing I want to show you is what I call a really cool feature. And Vault aims to be this like centralized secret store. And because of that, we don't want, users of Vault, we don't want you to have to write security things. And one common security tool is TOTP. Which is the general algorithm for multi-factor authentication, those 6 or 8-digit codes that you have to enter to log into some websites. And Vault can act as a TOTP provider. So instead of writing the code that will generate those, validate those, the QR code that you have to scan, Vault will do all of that for you. So I'm going to show you that real quick. So I'm going to enable the TOTP secrets engine. And then I'm going to create a key. So I'm going to write to TOTP key Seth. So I'm creating a key for myself. I'm going to tell Vault to generate it. The issuer is going to be my cool web app. And then my account name is just going to be my email address. Whoops. It helps if I spell right correctly. So what I get back is this kind of large thing. I get back a barcode, and I get back this URL thing. So this barcode is actually a base64 encoded PNG. So I can echo this. Whoa. And I will save this to a file. So I'm taking that, decoding it, and putting the decoded result into a file. If I open this QR code, I have a QR code. You're supposed to be impressed. No, that's not the impressive part. The impressive part is, so I have this cool website over here. What I can do is I can actually use, I'm using 1Password here just for demonstration, is I can scan this QR code. Boop. That was me, that was not my computer. And I'll get, this is an actual TOTP code, so I can copy this to my clipboard, and then I can verify that code. What did I name it? Seth. and that's true, and about 20 seconds from now, it'll be false. So instead of building all that yourself, you can just do this to Vault, and every command that I've run here today is an API call under the hood. So you don't even need to have Vault installed. You can hit Vault's API automatically, and there's a ton of client libraries and stuff. There's actually nothing that I did here today that you can't do through the API, and that's because the only way to interact with Vault is through the API. Apparently, I quit my presentation. Cool. That is all I have for you. Thank you very much.